And yeah, a lot of the slides are actually made by them. So yeah, thank you for sharing the slides with me. All right, so today we'll be talking about diffusion models. You might have seen that it's perhaps one of the most exciting technologies in generative AI. We've been able, over the last few years, to build incredible systems that can generate very realistic media content, images, videos, speech. I've mostly been working on generative models of images and things like text-to-image models, where you can provide an input like something, the caption that you see here, in a fantastical setting, a highly detailed furry humanoid skunk with piercing eyes confidently poses in a medium shot wearing an animal hide jacket. And you can get the diffusion model to generate an image corresponding to this caption, and you can get results that look like this. So pretty incredible level of detail, very, very very good quality images that are pretty well connected with the kind of description that is provided by the user. This is actually produced by one of the most recent models that we created, which is basically a stable diffusion that has been fine-tuned with the RLHF kind of techniques. So DPO, another technique that we developed for incorporating human preferences in diffusion models. So this is the paper if you want to read about it. Another example, I like coffee, so we tried to come up with some crazy caption asking the model to generate something like this, and I'll let you read the caption, and then you can imagine what would something like this look like, and you can get the models produce something like this. And so pretty incredible results. Never would have thought that we were going to be able to build systems that work so well. And really at the core of all of this is a generative model. It's a probability distribution over images that understands which settings of the pixels are likely and which ones are not. We can use these models and we can prompt them in different ways. It's not just we can control them not just through captions, we can control them through sketches. We can say, okay, generate me a pretty image that kind of corresponds to the sketch that even I would be able to draw, like the ones you see on the left, and then you can get the model to start from the sketch and make it much preserve kind of like the semantic content that you see on the sketch, but make the image much better. And yeah, as I mentioned, kind of like the underlying technological advance is better generative models, which are just probability distributions over complex high-dimensional objects like images. Underlying all of this, there's some underlying data distribution that essentially determines which assignments to the pixels in natural images are likely and which ones are not. And what we do when we want to build a good generative model is we try to come up with a good approximation of this data distribution. And this is what we call the generative model, a deep generative model. And once we have access to it, we can basically use it to sample to generate new content. And especially what we really care about is controllable generation. We want to be able to control the generative process through captions, sketches, and so forth. And of course, this idea is pretty powerful. Once you have a system that can kind of start from a data sets of objects you like and learn a probability distribution over this data set, and then you can use it to sample to generate new objects that have the kind of desired properties, that have the right structures. There's been a lot of excitement around using generative models, and in particular diffusion models, for generating new molecules. You can train a generative model or a database of molecules, and you can get the system to generate new ones. Again, you can do controllable generation. In this case, we're not controlling through captions, we're not controlling through sketches, we're controlling maybe the kind of properties that the molecules we want the system to generate should have. And we can work at the level of graphs, like which atoms, which bonds the molecules should have. In this talk, we'll talk about actually working at the level of the geometry of the molecules, how to develop diffusion models that can really understand the position of the atoms in a 3D space. And it's not just small molecules. People are getting some really cool results in training these kind of generative models on large kind of organic compounds, like trying to design proteins, trying to design antibodies, trying to design a lot of interesting objects that can be very useful when you're thinking about designing new drugs. And so there's a lot of excitement about using diffusion models in these kind of scientific applications. So how does a diffusion model work, and why is this an interesting technical problem? Well, the challenge in modeling these kind of like complex data distributions, whether it's molecules or whether it's images, it's that we're trying to model a distribution over a high-dimensional space. There's lots of different configurations of images, and we need to somehow be able to assign a probability that makes sense to all of them. So classic cursive dimensionality kind of problem. And so it's tricky to come up with a model distribution that is sufficiently flexible to describe the complexities of the original data distribution. Of course, it's easy to come up with simple model distributions, like we've been building generative models or statistical models for a very long time. You could try to fit simple distribution, like let's say a Gaussian, which you can think of it as a very simple neural network that will basically take as input an image or a molecule described in some way, a vector, and then maps it to a scalar, which is just the probability assigned by the model to this particular input point. And a Gaussian is a simple type of generative model where the kind of like computation that you do to go from the input to the probability is very simple. It's just like the usual expression for a Gaussian PDF that you see on the right. And this is a useful model for a lot of applications, but it just doesn't cut it if you're trying to model a distribution over images or molecules. It's kind of like too simple. It has a single mode. It doesn't capture the complexities of the data distribution. And so what we want to do is we want to use deep neural networks to model this function that assigns probabilities to different data points. And that's kind of like the idea behind deep generative models. But designing a deep neural network that assigns probabilities with a high-dimensional input space is non-trivial because probability density function needs to satisfy a bunch of constraints, has to be non-negative. If you take an arbitrary neural network, the output might be negative, and so you can't really think of it as a probability. You need to make sure that the output is non-negative for every possible input, which is not hard to achieve. You can just apply some non-linearity at the end that makes the output non-negative. The more difficult constraint to satisfy is that it has to be normalized. So if you integrate over all possible inputs, you have to get one. And that's a much harder constraint to enforce. If you take an arbitrary neural network, it's not going to satisfy that constraint. And so you cannot really think of it as a probability density function. One thing you can do is you can kind of think of it as an energy-based model, or you can equivalently kind of like normalize by the normalization constant that you see there, the z theta, the partition function, which is just the integral over all the possible inputs of the unnormalized probability. This defines the valid probability density function, and sometimes it's easy to compute. If you have a Gaussian density, the normalization constant is just the denominator that you have in the usual Gaussian PDF, so you can kind of compute it analytically. But if you have a complicated neural network, computing the partition function involves some high-dimensional integral. You can't really evaluate this quantity, and it's very hard to kind of compute it and build a proper probability density function using an arbitrary neural net. It's hard to compute, and there's been a lot of work in physics and other disciplines in trying to approximate this quantity. So one way the diffusion models kind of get around the complexity of dealing with the partition function is by kind of like bypassing it completely by working with the score function instead of working with the likelihood, with the probability density function directly. So what do I mean by that? Well, if you try to model a probability density function, you're kind of like trying to think about a family of functions that are normalized. You can kind of change the shape, but you need to make sure that the area under the curve is 1, right? So no matter how you choose the parameters, it has to be a valid probability density function. And in order to do that, you have to normalize. Like if you define an arbitrary non-negative function, you have to be able to somehow compute the area under the curve and divide by that to define a valid probabilistic model. Now, what we can do is we can work with the score instead, which is just like the gradient of the log of the expression of the curve you see on the left. in this case, the gradient is just a derivative because everything is one-dimensional here. But you can kind of see that the score or the gradient of the log of the PDF that you see on the left is a simpler function to work with. And in particular, if you look at the math, if you look at the log of the probability density function that we have on the left, you're going to get two terms. You're going to get the neural network f theta, and then you have this log normalizing constant, which is the annoying piece that we don't know how to compute. But crucially, the log partition function does not depend on x. It's a constant. It's the same. The area under the curve is the same, regardless of where you are, regardless of the value of x. So when you take the gradient with respect to x, that evaluates to 0. And so it disappears. And so we can kind of like see that the score function does not depend on the partition function. And so intuitively, it's going to be a lot easier to model. It's going to be a lot easier to work with the score function instead of the probability density function itself. And so that's kind of like the idea behind score-based models, which is kind of like the main idea behind diffusion models. Instead of working with the probability density function, we work with its derivative, essentially, the score function. And so if you think about it in 2D, a probability density function could look like, corresponding to, let's say, a mixture of two Gaussians, would look like this density plot that I have on the left. The score function is kind of like the function that you get by taking the gradient of the density at every point. And so at every point you get a gradient, which is a little arrow that is giving you the direction that you should follow if you want the log likelihood to increase most rapidly, right? So you can see all the arrows that are kind of like pointing towards the two modes of the density P of x that I'm showing here. And even though they are equivalent, because if you can always get the density by integrating the log likelihood, it's going to be more convenient computationally to work with the score because, again, it does not depend on the partition function. So now, given this intuition that we want to work with score function, we need to still figure out how to actually build a useful generative model. We need to figure out how to learn score functions from data, and we need to figure out how to use score functions to actually generate new data points. And this is where the idea of diffusions come in. A diffusion model essentially starts with a process that takes data and destroys the structure of the data by progressively adding noise. So you can imagine a process where we start with a data point, and then we progressively add noise to the data until we destroy the structure completely, and we're left with pure noise. We can describe this kind of process using a simple stochastic differential equation, where essentially, if you were to discretize it, this process would correspond to the kind of to a relatively simple kind of dynamics, where at every step we add a little bit of noise to we start the process with a data point, and then we add a little bit of noise at every time step. And for every t, for every point in time, this defines a new version of the data distribution called PT, which is just like the data distribution convolved with the amount of noise corresponding to the effect of running this diffusion process up to time t. Now, why is this useful? Well, you can see that this process goes from data, which I'm showing here on the left of this plot, all the way to pure noise. And you can see kind of like the density goes from something that looks like a mixture of two Gaussians, where most of the probability mass is concentrated at these 2 points, and then slowly the structure is lost, and we get pure noise at the other end of the time horizon. Now, if we could reverse this process and we could go from noise to data, then we would be able to generate new samples. That's basically generative modeling, going from noise to data. And it turns out that if you have access to the score, then we can reverse this process. So if you think about the flipping the direction of time and going from time capital T to 0, going from noise to data, then this process, which is just running basically solving the stochastic differential equation in reverse time, would correspond to a sampling procedure that takes noise and transforms it into samples. And crucially, it can be shown that the reverse time SDE that goes from noise to data can be described analytically in terms of the score function. So if you have access to the score function of all these densities that you get over time by basically convolving the clean data with noise, then you have access to the score function, and you can, in principle, solve this reverse stochastic differential equation, and you can turn noise into data. Now, how do we estimate scores from data? How do you go from data points, a bunch of samples from a distribution, to...
One second, we have a question from the room.
Yeah.
So I'm, I know this is how diffusion works, but I'm just wondering, in order to reverse that process, it seems that you could not have been using random noise. So what kind of noise are you using?
Are you thinking of the initial noise that we used to initialize the process, or the one that we added every step through the stochastic differential equation?
The one that you added every step.
It's again, it's just another Wiener process. So you can actually even, turns out you can actually convert it to an ordinary differential equation that basically satisfies the same.
My question is, if it were stochastic noise, you couldn't reverse, based on a random process, you would not be able to.
Good question. So this is defines the same process in the sense that it has the same marginals, which is all we care about.
Okay. Thank you.
Yeah. And so if we had access to the score function, then we could, in principle, sample from this procedure. And the question is, how do we get the score function? We know how to estimate densities from data. That's the usual kind of like maximum likelihood thing, where you just fit a function and you choose parameters to make the data as likely as possible. How do we get a score function from a bunch of data points? And so that's kind of like the problem. You're given a bunch of samples from a data distribution, which you don't know. And then you try to estimate the vector field of gradients of this data density. And we do it by defining a model. Think of it as a neural network. It's a vector valued neural network. So d-dimension in, d-dimensions out. And we try to choose parameters data so that it's as close as possible to the true vector field of scores. And how do we compare two vector fields? Well, there is a true vector field, there is an estimated vector field. At every point, you can kind of look at what's the true vector field, what's the estimated one. You can look at the difference. And if you have a good model, these vectors should all be small. So one way to define a loss function is to basically look at the average size of these errors and try to make it as small as possible, right? So you can kind of look at the magnitude of these errors, average them, and define loss functions you can try to minimize as a function of data. So that's the so-called Fisher divergence, where you average with respect to the data distribution of the L2 distance between the true score and the estimated score at every point. This looks like something you will never be able to evaluate or optimize because it depends on the true score function, which is unknown. We only have access to samples from the data distribution. Turns out you can do integration by parts, basically, and you can convert it into an equivalent loss function up to a constant, which only depends on the model. It no longer depends on the data density. And you can approximate the expectation with respect to the data distribution with the training set, sample average, or the training set. And this defines an objective function that you can optimize as a function of data, as a function of your neural network. Now, this is not quite scalable because it involves higher order, this trace of the Jacobian term, which is kind of like expensive. But there is another version of this, which is called denoising score matching, which maybe I'll go through quickly since time is running fast here. But essentially, there is a way to reduce the problem of estimating the score to a denoising problem, where essentially, because we're dealing with this kind of like very special case where we're trying to estimate the density of a data distribution that has been convolved with Gaussian noise, then it turns out that it's possible to reduce the problem of estimating the score to essentially a denoising problem, where you can equivalently train a neural network to take a noisy image and try to predict what was the clean image corresponding to that noisy image. And the best way to solve this denoising problem is to basically estimate the score function of the underlying noise perturbed data density. Kind of like, okay, I don't have the slide here, but there's something called Tweedy's formula that basically relates denoising problems to score functions. And essentially, the best way to denoise an image is to kind of like follow the gradient of the log likelihood of this noise perturbed distribution Q sigma and try to go towards higher probability regions, essentially. And so that's kind of like where the connection between scores and denoising shows up. So that's great because denoising is a relatively simple problem. We can train neural networks to solve denoising tasks. And by doing that, we're learning the score. And if we're doing a good job at estimating the score, and you can see here, it's a very simple loss function where you start with a data point, you sample a noise vector z, you add the noise to the data point to get x plus sigma z, which is the noisy image. And then you train the model via regression, basically try to predict the noise or equivalently predict the clean image x. And if you can do that, this provably basically is the same thing as trying to minimize the Fisher divergence between the score model and the noise perturbed data density corresponding to a certain noise intensity. Now, if you can do this, then basically you can just take that reverse SDE, you can replace the true score function with the estimated score function, and you can get a generative model. You can start from noise, and you can follow these the directions that are basically given to you by the score function over time. And you can see that it's basically progressively denoising pure noise vector into a clean sample. And you can see here kind of like an animation showing you the process where you start from pure noise, then you slowly get to clean samples. These are two models trained on CIFAR 10 and Solid.
You have another quick question here?
Yeah.
Who first invented this methodology for generative images?
It's a good question. I think there's a 2015 paper called Diffusion models, where they had something similar, but it was discrete time and they were not actually doing denoising. We had a paper in 2019 that basically did score matching and did something similar, but we were not sampling by using a reverse SDE. We were actually doing more like MCMC. So it was a different kind of, or equivalently, you can think of it as a different kind of solver for the SDE. It was like a rector only kind of thing, a neo-Langevin dynamics kind of thing. And that's kind of like the first paper that sort of like showed that score matching can be used, and you can get high quality samples on images. I think that's the first kind of method. The first paper demonstrating that modeling the score function can get you high quality samples on images. And then this ODE, SDE, it's another paper that my student Yang Song was the first author on, as a collaboration with Google that I was also part of, where we actually figured out this connection with the ODEs and SDEs, and kind of like thought about it from the stochastic process kind of perspective, and kind of like unified a bunch of the existing techniques that were people had thought about before in terms of like using score models and diffusion models, and kind of like highlighted all the connections between them. Score matching itself was invented before, so of course lots of people contributed to this idea.
Great, thank you.
All right, now, and this is really the kind of like key idea behind Stable Diffusion, ImageNet, DALL-E 2, Midjourney. A lot of these extremely good image generation systems are kind of like based on this kind of sampling procedure. You start from noise, turn it into a clean sample by following scores or progressively denoising clean noise into a sample. So far we talked about score-based models and how we can avoid the normalization process, the normalization constant, very flexible, gives you high quality samples. Now what I want to talk about next is I want to show you how you can actually, these models are quite useful because it's very easy to control the generative process. Right, and so the idea here is that if you have a prior distribution, where let's say images, where there's for simplicity, think of two kinds of images of cats and images of dogs. If you have some kind of classifier, P of y given x, that can classify images into either dogs or cats, the question is there a way to control the generative process to get the model to output images of, let's say, dogs? And mathematically, what we want here is the combination of the prior and this likelihood to define the corresponding posterior distribution, P of x given y, which is basically the way you would have to modify the prior to take into account the fact that we only want images x that are going to be, let's say, classified into the label y equals dog. And this is the posterior distribution, the inverse distribution, and would like to somehow be able to sample from this. And there's a lot of applications of this that I'm going to show you next. For example, inverse problem solving, where this is very useful. And the posterior distribution is just defined trivially through Bayes' rule. It's just what you get by multiplying the prior with the likelihood and then normalizing it to get a valid probability density function. And it's deceptively simple. The numerator is just a product of two functions. The problem is that, and this is why Bayesian inference is hard, is that once again, we are in this situation where the denominator is tricky to compute. It's kind of like the partition function, the normalization constant that we had before is exactly the same problem. You have to normalize, and computing a normalization constant is very expensive. It requires some high-dimensional integral. But if we look at what Bayes' rule will tell us, if we look at the score functions, once again, the denominator disappears. So if you look at if you just take the log of the expression that I have here, you're going to get that the log of the left-hand side is equal to the sum of a bunch of logs of the log of the prior plus log of the likelihood minus log of the denominator. And crucially, you can see that the denominator P of y does not depend on x, just like the partition function did not depend on the actual point you are at. The normalization, the denominator is just a constant with respect to x. So when you take the gradient with respect to x, that disappears. So what this is telling us is that if you want to get the score of the posterior, all you have to do is you have to just sum up the score of the prior and the score of the likelihood. And so if you have a pre-trained generative model that is parameterized using the score, you can combine it with any likelihood function. To the extent that you can compute the score function of this likelihood, you can get the score of the posterior, which means that there's a plug-and-play way of basically taking a generative model, combine it with a likelihood, and sample from the corresponding posterior, which is what we can use to basically control the generative process. And a classic application of this is inverse problem solving. Right? If you imagine the problem of super resolution, let's say I give you that very pixelated, very low quality image, and I ask you try to recover a high resolution version of that image. It's an ill-posed problem, but we can think of it. We can think of the problem of inverting the downsampling operation probabilistically, and having a good prior over what high-resolution images look like is going to be very helpful. So you can imagine starting with a prior of what images of people look like. We can combine it with a likelihood, which in this case is going to be very simple. It's just like, what is the relationship between a high-resolution image and a low-resolution image, and we can check how consistent they are with each other just by basically, it's a simple mathematical operation to go from x to y. It's just a downsampling operation. And we can combine these two objects to get a posterior that will basically tell us which images are likely under the prior and are consistent with the kind of measurement that we have with the corresponding low resolution image that I'm showing you here. And then if you can sample from the posterior, then you are solving the super resolution problem, right? And the good thing is that if you have a good prior, if you have a good model that tells you which images are likely a priori, then you can get some pretty good results in a variety of different inverse problems. So classic example is in medical image reconstruction. CT scans, MRIs basically involve solving an inverse problem where you get some measurement from the machine. You kind of like a projection of the actual body shape. And what you want to do is you want to infer the corresponding like medical image given this projection. And crucially, the more measurements you want to get from the machine, the more radiation you have to give to the patient. And so we would like to be able to reconstruct the medical image using as few measurements or as little radiation as possible. And we can think of this as an inverse problem. And what we've shown is that using score-based diffusion models, you can get really good results in CT scan and MRI also reconstructions by basically using a very good score-based diffusion model as a prior over medical images, combine it with the likelihood, which is known exactly in this case, it's whatever the physical process corresponding to CT scan or MRI looks like. And we can do medical image reconstruction by basically sampling from the posterior. And I'm going to go through it a bit quickly, but essentially what we get is very good results, outperforming even competing methods that were trained specifically for this task of medical image reconstruction. Now, the same machinery can be used on more other kinds of inverse problems, like what I showed you before, going from stroke painting or sketches to images. Again, you can start with a prior of what nice images look like. You can combine it with the likelihood that that kind of like gives you the relationship between the image and the sketch, and you can use it to stroke painting to image. This is exactly the technique that we used to generate these kind of results, where the measurement in this case is the sketch provided by the user, and the image we're sampling from is a clean, high-resolution, nice image that is likely under the prior and is consistent with the measurement given by the user. And we've used this kind of machinery to solve a variety of inverse problems, super resolution, in-painting, deblurring. A lot of inverse problems are actually linear, which makes our life even easier. So if the measurement process is some kind of like linear combination of the true image that you're trying to reconstruct, x0 plus some noise, then it's actually possible to solve linear inverse problems very efficiently using a diffusion model as a prior over the clean data, over the signal you're trying to reconstruct. I'm not going to go through it in a lot of detail, but the basic idea is that at the core of a diffusion model or score-based model is some kind of denoiser that takes a noisy image and tries to predict what is the corresponding clean image. And if we already know, let's say, a subset of the pixels of the clean image we're trying to reconstruct, because we have a measurement, like if we're trying to do in painting, the measurement y, it's kind of like a subset of the pixels of the image. And if you already have that kind of information y, then it's relatively easy to combine it with the prediction from the score model, from the denoised image that is being predicted by the score model. You just basically replace all the pixels that were predicted by the score model with the true pixels that we know we're trying to, the image we're trying to sample from. We know their values, right? So if you are missing the central crop of the image, but you know all the pixels around it, when you use your denoiser, you can just replace all those pixels with the ground truth, and your life is a lot easier. Now, this is only true if you don't have measurement noise, but there are ways to basically incorporate measurement noise, and you can get some really good results using this technique. Here are some of the kind of results that you can get using a pre-trained diffusion model, combine it with different kinds of likelihoods. There is no training involved. It's purely an inference kind of thing where you can do super resolution, you can do in-paint, you can do deblurring, you can solve a lot of different inverse problems really well just with a plug-and-play technique, or you have a really good prior, you combine it with a likelihood, you have a good inference technique, and you can do really well in these kind of problems. And there are interesting applications of this also in the sciences. There's been applications of this technique called DDRM, the noise diffusion restoration models that I just talked about in astronomy. We are looking into applications in remote sensing. I do a lot of work on satellite images, and turns out you can use these techniques to reconstruct high-resolution satellite images from infrared measurements from satellites, or low resolution, kind of like RGB measurement from satellites. You can see here some of the examples of you can start from this low resolution view of allocation of the world, and the fourth column here is the ground truth, and the hours column is kind of like what you can get using a diffusion model, and kind of like solving an inverse problem, trying to reconstruct a high resolution image using these kind of techniques, which is again some kind of super resolution inverse problem where we can get extremely good results using diffusion models that are trained on satellite image. Now, the thing I want to talk about next is how to incorporate constraints in the generative process. So far, we're kind of everything is data driven. We are sort of like training a prior on the data and then maybe do inferences. But what can we do if we know something about the structure of the data? Maybe we know that, for example, that the data, we know something about the support of the data distribution. We know that the data lies in some kind of set, and we want to be able to satisfy these kind of hard constraints through the generative process. How do we do that? And as a recap, we often want to use these kind of diffusion models in a guided way where we combine a prior and likelihood. And what can happen is that things can go wrong. These are some examples from the Imagen paper that are in the appendix from their the Imagen is one of the diffusion models that was trained by Google. Sometimes the diffusion model produces these really bad samplings if you don't do if you just naively apply this kind of technique. And the reason is that there are approximations involved. Like whenever you're trying to solve this reverse time stochastic differential equation, you're replacing the true score with an estimate, and you're also discretizing the time dimension because we cannot work with continuous time. And both of these things actually introduce errors. And essentially what happens is that as you kind of like try to follow and reverse the sampling procedure, sometimes the trajectories will go to low probability regions where essentially the score function is not going to be learned very well, and then this might take you in very weird parts of the data space where you don't have good information about how you should change your samples to go towards high probability regions, and the whole sampling procedure can diverge, generating really low quality samples. So the question is there a way to kind of like constrain the sampling procedure to stay within regions where we know that the data actually has to be? And what people do in practice is they threshold what they apply some simple thresholding rules to enforce kind of like known constraints on the data. So what they do is they start from this basic kind of like discretization of the SDE, and then essentially whenever this update rule will get them, let's say, out of the domain where they know the data lies in. So if we're working on images, we know that the pixel intensities, let's say, after normalization have to be between -1 and 1. And so if this kind of stochastic procedure is going to push you out of this constraint space over which we know the data must lie in, then they just apply a simple projection to basically push the samples back in. And then you keep going, but if at every point kind of like the sampling procedure takes you out of the known support of the data distribution, then you push the samples back in. And this is what people do, and it's very important that you do it. If you don't do it, the methods just break down. And here I'm showing you how it's actually implemented in a lot of the key kind of like diffusion repos that you can find on GitHub. You do have to clip, you do have to clamp, otherwise you get this really weird kind of sampling effects like these ones that I was showing before. Like this is what happens if you don't do it. You get very, very, very weird results. And what we did in a recent paper is we kind of like looked at into what's the right way of applying these kind of constraints, right? Well, the problem is that if you just during the reverse diffusion process, you apply this clipping, there is a mismatch between the forward process and the reverse process. And the way to correct it is to basically really realize that this thresholded diffusion process is no longer just a regular stochastic differential equation or a regular diffusion process, but it's a reflected diffusion process. And so in particular, what happens as you make the discretization time go to 0 is that this process of constantly projecting back the trajectory into the known domain space kind of like corresponds to a new stochastic process where there is a boundary condition and the samples can never go below this kind of boundary. It's a reflected diffusion where there is a boundary, and whenever you hit the boundary, you're being reflected back. And what we've shown is that it's possible to use the same kind of like forward and reverse diffusion idea. But what we should do is if we're using a reflected diffusion when going from noise to data, we should use a reflected diffusion also in the forward process when we go from data to noise. And that's kind of like the key idea of this paper that we presented at ICML in the summer, basically replacing the typical diffusion process that you use to go from data to noise and from noise to data with two reflected diffusions, where there is a boundary condition that is basically enforcing these known constraints that we suppose we know the data satisfies. If we know the data is always going to be between -1 and 1, we want to make sure that all our trajectories never cross the boundary. So we're going to use a forward process, noising process that is described by a reflected diffusion, and the same thing for the reverse process. And I think I'm running out of time, so I'll skip some of these details, but essentially you can still do denoising score matching. You just have to change basically the transition kernel, but there is a way to kind of like extend the score matching idea and apply it to these kind of transition kernels where you have a boundary condition. And there are ways to make this efficient using harmonic analysis. Again, I'm going to skip it. But the end result is that this actually improves the sample quality because there is a better match between the forward process and the reverse process. You can improve sample quality metrics like inception scores on classic data sets like CIFAR-10. And it actually helps you deal with controllable generation settings. If you have some kind of like classifier that is trying to push your samples to be consistent with some measurement, thresholding can still cause problems. As you can see here, these images are not very natural. But if you have this process that is kind of like taking into account the fact that there are boundaries and you want to reflect whenever you hit a boundary, we can actually do much better at controllable generation, and we can generate images that are much more consistent with the prior and the likelihood, which in this case is just a plus label. And it also improves likelihoods because we basically know that all the probability mass has to be over a known support set, let's say between -1 and 1. We can help the model give better probabilities to the data point, and we can improve basically the kind of the fit of the model in terms of likelihoods, again on classic data sets. And now I think I'm pretty much out of time, so I'll maybe just say that, yeah, this can be generalized to other geometries. Another thing that I didn't get to talk about, but I think maybe it's a good time to, I'll just quickly go through a few slides, but The other thing, the other type of prior knowledge that you often have in scientific applications is not just kind of like constraints over the support of the data. Like we know that the data has to be between -1 and 1, or the kind of quantities we're modeling are non-negative, or things like that. Another kind of like typical type of prior knowledge that we have in a lot of real-world scientific and engineering applications are symmetries. Like when you're trying to model molecules, for example, we know that there is rototranslational invariance. So if you take the 3D structure of a molecule and you rotate it or you translate it, it's really the same object. And so it should be assigned the same probability by the generative model. And we've been kind of like building variants of diffusion models where the probabilities assigned by the model, I guess this is a mistake, it should be, they are invariant to rototranslations over when we're dealing with geometric objects like molecules. And basically what you have to do if you want to build models that basically respect this kind of like natural symmetries of geometric data, or at least one way to do it is to basically define a diffusion process where the transition kernels respect these symmetries at every time step. And one way to do it is to basically define certain kinds of parameterizations of the neural networks that you use to define the score model, using certain types of neural networks that are known to respect these sort of equivariances. And incorporating these kind of constraints, we've been getting some pretty good results here. This is our GeoDiff model, diffusion model for geometric data that incorporates these kind of invariances, and we've applied it to molecule data sets, and we can use it to generate molecules that kind of have the right structure. And it's here you can see some examples, but I'll go through it. I'll just skip this part, but it works quite well at generating the conformation of molecules given their structure, given their graph representing the atoms and the bonds. And yeah, we've also extended it to settings where you're also trying to figure out what the atom types should be using latent diffusions, but I'll kind of skip through this. It's a similar kind of idea, diffusion model, just do it over a latent space. And again, works pretty well. You can use it to generate molecules with known properties. Like, again, you can do controllable generation, and if you have a model that can predict, let's say, how polarizable a molecule is, you can use that to control the generative process, and you can try to push the generative procedure to generate molecules that are not only likely under the prior, but they are consistent with this measurement, in this case given by another machine learning model that predicts some kind of interesting properties of the molecules that you might try to optimize. And yeah, I think this is probably, I think I'm kind of out of time, so I want to leave some time for questions, but kind of like a high level takeaway is hopefully I convinced you that diffusion models are a really good type of generative model for several reasons. One is that you can, working with scores, really gets around the normalization constant, which is very important from computational reasons. And it works quite well in terms of sample quality. And especially, it's very, very natural to, and it allows you to do controllable generation in a very natural way, because you can combine scores just by basically summing them up. And so it's very easy to build models where you can condition on text, or you can condition on labels, or you can solve inverse problems using this kind of machinery in a plug and play way. You can take a pre-trained model, you can combine it with a likelihood, and by solving the inference in the right way, you can get some really good results. And yeah, other things that I think are pretty exciting if you're thinking about applications of these ideas, especially on scientific and engineering problems, are things like, okay, how do we incorporate constraints? And we've made some progress on that. We're working on geometric data, incorporating symmetries. Again, there's a lot of exciting work happening in that space. Incorporating preferences is also an interesting kind of direction, so reinforcement learning from human feedback, that we're starting to look into that. And again, it has applications in scientific problems as well, where you might have like a big data set of different types of things the model could generate. You can get feedback from humans or from other AI models to tell the system which generations are preferable and which ones are better than others. And then you can kind of try to infer the preferences and then steer the diffusion model to generate the things you like more frequently than the things you don't like. And discrete data, it's another thing that I'm personally very excited about, how to extend these kind of ideas that are very continuous, like we're working with gradients and things like that. How do we extend it to discrete objects? And, we have made some progress on that, because if that works, I think that would open up a lot of other interesting applications, including language, but there are other sort of things like DNA sequences that are very naturally thought in terms of like discrete objects, and we're getting some pretty good results in training diffusion models specifically for discrete data. And yeah, I think it's probably a good time to stop, and I'm happy to take questions.
Yeah, so it looks like we have a question from the chat. In the chat, Elton Z asks, do you have any thoughts on classifier-free methods versus classifier guidance for guided generation?
Yeah, it's a good question. I mean, it seems like empirically classifier-free guidance tends to be better. It's expensive because you basically have to train two models, and so in some settings that's a problem, and it kind of like requires you to train a conditional model, and so you're kind of like giving up on a lot of the flexibility that you get if you just combine a prior with a likelihood. So in general, if you can afford to train a conditional model, that's better. But training these models is very, very expensive. Like it can cost, you need hundreds of high-end GPUs for long, and you need to use them for a long time. And so I think like the flexibility of being able to take a pre-trained model and combine it with other pieces in a principled way, just think of it as an inference problem, is quite nice, especially when we have limited computational resources. I think people in the industry, maybe they can afford to just train conditional models for every different use case. But yeah, when we are GPU poor, then I think classifier guidance is still a pretty useful kind of tool to know and use, but still works pretty well.
Okay. Yeah, thanks for the great talk. So I have a question. So I think the advancements of using the score instead of your probably entire marginal probability distribution is a great idea. And do you have any comments on extending this to a lot of problems maybe already in science? Because we have a lot of stochastic process or PDEs we already know. Maybe that could help as the computational efficiency as well. Do you have any comments? It's just
I think I've started to see people kind of using these kind of ideas to like in science and engineering problems as either models to try to guess the solution of a PDE or also as a combination where they're trying to maybe have a generative model and then they combine it with some known equations and try to kind of like get the best of both worlds. One thing that I didn't really talk about is that learning and inference are decoupled in score-based models, because you just learn your model, which is kind of like weird. It's very different from the typical deep learning folklore, where you always have to couple learning and inference, and you always need to use at inference time the same exact procedure you did at training time, so that there's no mismatch between the two, and that typically is the best thing to do in according to the deep learning wisdom. Here it's decoupled. Like you can train a model, and then there's many different kinds of inferences that you can use at test time. Like you can solve an SDE. Turns out you can also solve an ODE using the score, and that's a different kind of inference procedure. And you can actually control the compute time. Like unlike other kinds of generative models where you cannot really decide how much compute you're willing to use at test time to generate samples. It's very natural to do this with diffusion models, because you're just solving an SDE or an ODE, and so you can control the discretization step. But there are other kind of, there's many decades of work on solving SDEs and ODEs, and you can leverage a lot of those ideas to decide basically at test time how much compute you want to use and trade off quality for speed. And so I think that's very, very nice in a lot of these applications where you really care about speed. And yeah, we're also pushing quite a bit in that direction, like bringing in like fancy numerical solvers for speeding up the sampling procedure, like paralleling time, kind of like sampling methods that I'm pretty excited about.
Yeah. Oh,
Hi, Stefano. I don't know, maybe you have to say, can you say
can you come closer so you can get caught on the speaker?
oh, is it up there?
Okay.
Hi. Oh. I don't know, I hope you can hear me. Yeah, so great, amazing stuff. Could your final point is sort of, can you move to discrete data language? Can you give us a bit of a sense of what the challenge is? I mean, it feels a very different because you don't have the natural gradients, etc., that you have in an image. Can you say a little bit of what kind of potential there is for discrete data?
Yeah, that's something I'm very excited about. I'm thinking a lot about these days. The thing that we are exploring is basically this idea that in some sense a gradient, it's kind of like telling you locally which changes to your data point will lead, and how to relate local changes to the data point to changes in probability, right? And you can define something similar in a discrete space as long as you have some kind of neighboring structure, some kind of you can kind of like the equivalent of a score function is basically like a density ratio, it turns out, that is kind of like telling you if I were to flip a token in a sentence, how would the probability change? And so we call that a concrete score, and it's just a density ratio. And if you were to, let's say, take a continuous space and discretize it, it would basically correspond to finite differences, which is kind of like the natural analog of what you would get if you were to discretize a score function, a continuous score function. And it turns out that the same kind of machinery can be applied there. So you can estimate these density ratios with score matching like objectives. And so, and the objective ends up being something like the clean data. In the discrete setting, what you do is you kind of like flip tokens, and then you try to predict what was the corresponding clean data. And it turns out that a lot of the ideas actually translate over pretty nicely. So you can still define some kind of like diffusion. Now the diffusion is over a graph because everything is finite. But there is still a process where you basically do a random walk on a graph, and eventually you end up with some kind of stationary distribution, which, let's say, it's uniform, and then you can invert kind of like the direction of time. And if you have access to the score, which is in this case just the density ratios, you can exactly reverse this process. You can generate samples by kind of like solving an ODE in that case in reverse time. So a lot of the machinery actually translates pretty well. We have a preprint out where we've shown that actually you up to GPT-2 scales, we can actually get better results compared to autoregressive generation. So with the same number of parameters, if you think of it as a discrete diffusion problem on language data, we can get better perplexities, so basically better likelihoods. Even though we're not training with maximum likelihood, we still get better likelihoods in the GPT models, and actually better generation, like using the kind of metrics that people use which are not perfect, but if you try to score the generations of your model using a more powerful generative model, essentially like a bigger GPT kind of model, we end up being better. So it's pretty exciting because we can do it with diffusion models, which means that we can control trade-off time for quality in a very natural way, which you couldn't do with the regular autoregressive generation. We can get much better controllable generation. So you no longer, like in an autoregressive model, you can kind of like control the generation only through a prefix, through a prompt. But when you use these kind of discrete diffusion language models, you can do arbitrary infilling. So you can condition the model based on prefixes, suffixes, any kind of controlling signal you want. So I'm pretty excited about this, and yeah, we're hoping to scale it up to larger scale models and see whether the trend continues. But up to GPT-2 level scales, it's competitive, slightly better than autoregressive generation, which is pretty exciting.
Very good, thank you.
Great. I think we're
Okay,
here.
I don't want to interrupt, but could I ask? I mean, I've been dying to ask this question.
There are
Okay, one more.
Everybody's dying.
No, no,
Okay,
no.
Luke wanted to die, so go ahead.
You started off this talk with the coffee cup portal to a fantastical dimension, which is, of course, what I see every morning. And but you never got to, you talked about conditioning on text data. This may have been embedded in your answer to the previous question, but I would really like to know just, it might be another hour-long talk, but how do you code that kind of textual data you had in the prompts as a constraint on your generative model? That's the question probably everybody has about generative models, which you teed up to answer and then left us hanging.
Actually, it turns out you can actually control the generative process reasonably well if you have if you think about it from the perspective of, okay, it's just an inverse problem, or you have a likelihood. Like, this is not how the stable diffusion is done, but if you have a P of Y given X, which is just a captioning network of some sort, let's see if I have it. What you can do is you can basically just do controllable, essentially just combine exactly this, basically, right? So if here P of C given X is some kind of like image captioning
That's
model.
fine. What I want to know is, how is the humanoid skunk in that equation? I understand the equations. I want to know how you took the text prompt and turned that into something that you could diffuse to.
Yeah, so it's exactly this equation. So essentially, there is a prior P of X, and then there is a clip model that basically tells you C is the caption here, X is the image, and the clip model tells you how consistent is the caption with the image. And effectively, what you're doing is you're steering the generative process to produce images that are likely under the prior, and that they are consistent with the caption, which is C in this case, provided by the user.
Okay, so you're saying in your training data, you have images that were classified as humanoid skunks.
So there is a generalization angle. So I don't think we had a humanoid skunk. We had captions of skunks. So we had images of skunks. We had images of humanoids. And then we're hoping that the model kind of like generalizes to captions it hasn't seen during training, just like we're hoping it generalizes to images it hasn't seen during training. So there is still some magic in terms of it has to generalize to X's and C's that it hasn't seen before. But fundamentally, this is how it works. You're just steering the diffusion towards images that are consistent with the caption.
Great. Well, we're almost 10 minutes over, so I think, fortunately, we're not going to be able to get to any more questions. But again, let's thank our speaker again for the wonderful talk.
Thank you.